So it's the second lecture of Clay. So please, Clay, when you are ready, you can start.
Okay, great. Thank you very much. I'll continue discussing symmetries and anomalies, and I'd like to pick up where we left off yesterday, continue on this theme for some time. So we were developing some basic examples of theories with higher form symmetry. So I remind you that we were discussing four-dimensional free Maxwell theory, which has two one-form symmetries. The first is this electric global symmetry, where the current is F mu nu, and the charged objects are Wilson lines. And the second one-form global symmetry was a magnetic one-form global symmetry. The current is star F, and the charged objects are 't Hooft lines. Okay, so this is a free theory, and you might have, while it's nice to have some results for the free theory, you might have limited interest in the free theory. So I'd like to tell you what happens, for instance, when you add charged matter to this. So let's include charged matter, and that will of course make the theory interacting. So the question is, what of the one-form symmetry remains? So let's look at a Wilson line. And this Wilson line carries some electric charge. Say the electric charge is positive. And as you probably learned in your field theory courses, when you have a source charge and you also have dynamical charges, then the dynamical charges will populate the vacuum to try to screen. So you'll, in a cartoon way, you'll get some plus minus charge pairs, which will arrange themselves to screen the Wilson line. So the nucleated pairs of dynamical charges arrange to screen the line. Now, what does this mean for our purposes? Well, imagine we tried to measure the charge of the Wilson line. The charge of the Wilson line for us is written up here. It's measured by integrating over S2, where the S2 surrounds the line. That was what this picture was that we discussed. Now, because of this configuration of nucleated pairs of charge, the effective charge of the line now depends on distance. Depends on how close you are to the line. Of course, you're familiar with this. This is just the statement that the electric coupling is now running because we have dynamical charged matter. But if we think about this from the point of view of symmetry, one-form symmetry is broken. The one that we called U1 electric is broken. Why? Well, I told you that one of the key properties of a global symmetry is that the U alphas, or in the continuous case, the charges, are topological operators. If they're topological operators, that means that in this equation, for instance, it doesn't matter what radius this S2 has. you can, as long as you're surrounding the sphere, surrounding the line, you can change the radius of the sphere. However, here, we've just argued from this picture that once we have charged dynamical matter in the story, the effective electric charge depends on distance. And therefore, the one-form symmetry is broken. Now, a little more generally, let's say the charge matter.
Sorry, Clay, I think there is a question by Lucas.
Sure.
Okay, it's about clarification. When you say broken, you mean explicitly broken or
explicitly broken?
Explicitly.
Look, I mean, we can let's be even more less pictorial, more equation oriented. In order for there to be the U1 electric global symmetry, we need d mu f mu nu equals 0. We need this current to be conserved if you want a U1 one-form global symmetry. That's true because of the free equation of motion. But if you add charged matter, divergence of F is not 0 anymore. There's something on the right-hand side. So it's just explicitly broken. The associated current is not conserved anymore.
Okay, thank you. I understand.
Yeah, I will take great pains throughout to distinguish explicit breaking from spontaneous breaking. But if that ever becomes confusing, please ask for clarification. Okay, so let's return here. So more generally, let's say the charge in our theory have charge Q, which is greater than 1. So, for instance, maybe we have some fermions in our Lagrangian, and they all have charge 5. Nobody has charge 1. So then I claim we get a kind of interesting intermediate situation. Then this U1, one-form electric symmetry, will be broken explicitly, not to nothing, but to a symmetry which is ZQ, where this Q is this Q. And what this means, if you think about this picture that I was drawing up here, means that we can only fully screen charges that are multiple of Q. So up here, if we look at the charge mod Q on the Wilson line, which is what this means, this is what I'm doing now. When I say that the U1 electric is broken to ZQ, it means I only now consider the charge mod Q of the Wilson line to be a good quantum number. We see that that can't be screened because mod Q, all our dynamical fields are neutral. Now, you might ask, technically, how would I check this? Let's test. If the charges are topological, if the associated alphas are topological. Okay. So we consider the exponential of I alpha integral over some 2 surface sigma 2 of star F. This was our U alpha for the U1 one-form symmetry, the electric one-form symmetry. And we'd like to see whether this operator is still topological in the presence of dynamical charged matter. So we should consider what happens to test the topological property, which is consider what happens if we deform this surface sigma 2. Multiply it by the same thing, except for I do a little wiggle on this surface sigma 2 where I'm doing the integral. Okay. Now again, I use Stokes in the exponent. So we'll now have some x3 where sigma 2 tilde together make the boundary of this x3 of J electric. So here, J electric is the current that appears in the Maxwell equations. D star F is equal to J electric. That's the new Maxwell equation. So here, to get this equation, I did Stokes, and then I used this equation of motion. So in the situation we're interested in, charge matter is a multiple Q, we'll be considering that the integral of J electric over any 3 manifold is a multiple of Q. So it's Q times something. So what do we want to find if we want this to be topological? If this is topological, this is supposed to equal 1. This is what we're checking. Now we use this over here on the right-hand side. See that this is true. We can achieve this topological property if alpha is 2 pi k over q, where k is an integer. So we see that the phase here is restricted. So we can consider U alpha for alpha qth root of unity. So that's the statement that there's a ZQ one-form symmetry in the problem. That's how we technically test and exhibit the topological operators. Okay, so learned about the one-form symmetry in Maxwell theory and in QED, where we have electrons of various different charges.
A small clarification. So in this equation of motion, F is a 2-form star F.
Yeah, sorry.
Right side.
Yeah, if you're right. Sorry, I'm mixing conventions here. If you think of this one form, then this should be star J. This is the equation of motion in indices is d mu f mu nu is j nu. And if I write it as different forms, it would be this one.
Okay, thanks.
Let's try to be consistent. Thank you. Okay. Good. So let's build up our arsenal of examples of theories with higher form global symmetry. And I'll discuss one more example, which is non-abelian gauge fields. So for simplicity, let's discuss SUN, Yang-Mills. One can do the same thing for other groups like SO or SP or your favorite group, but I will stick right now to SU. And just at the outset, I would like to emphasize that the global form of the gauge group will matter. So by that, I mean SU2 versus, say, SO3. Everyone knows that these have the same Lie algebra. So locally, these groups look the same, but globally they are different. And for us, while often you get to ignore such small differences in talking about quantum field theory, here they will really start to matter. Okay. So what are the Wilson line operators? I'm eventually going to tell you that Yang-Mills has some kind of one-form global symmetry. And so the charged operators will be lines. So it will be good for us to do a little bit of a lightning reminder of what the lines are in SUN Yang-Mills. So the Wilson line operators these are in one-to-one correspondence with representations of the group SUN. And here you see, for instance, that this right-hand side, the representations of SUN, it really knows what the global form of the group is. So this is one place where the global form of the group is really entering. So these are, of course, all made from mental. So, you could have an N representation, typically written as a box in Young tableau notation. You could have the symmetric square of the N, that's two boxes arranged this way by convention. You could have the anti-symmetric square, that's vertically. You could have the adjoint. These are some commentations that I'm telling you. That's something like this, where there are N1 there, and so forth, some common representations, and each of them is some kind of Wilson line operator that we could consider. It will be important for us to know that the center of the group SUN, what is this? So this is matrices of the form lambda times the n by n identity. So this is the identity matrix. Okay, first of all, maybe I should say, what's the center? It means commutes with everything. And here, in order for this to be an UN, lambda should be an nth root of unity. So in SUN, there is this nice Zn subgroup. So I'll say it here. This is the Zn center of SUN. There's a Zn subgroup that commutes with everything. And so when we're looking at representations, we can think about how do they behave in particular under the center. And that leads to a kind of term of art here that is common. So I'll write it down, a definition, which is that the n-ality, so-called n-ality of a Wilson line or representation, if you like. This is its charge under the center. So you can also think that this is the number of boxes in the tableau modulo n. So so just to be clear, the n-ality is something that lives in Zn. Okay. So if we're going to think about one-form symmetry in Yang-Mills theory, we should think about, as I motivated from the abelian discussion, we should think about what lines exist, what charged matter exists, and what can be screened with the dynamical charged matter. So in pure Yang-Mills, by that I mean we have no matter, no explicit matter fields, no quark fields. We just have the SUN gauge group. Well, the only fields are the gluons. And these are in adjoints. So if we come up here to look at the adjoint, this was the adjoint here, and you see that adjoint representation has n boxes total. It's got n minus 1 in this long column and 1 over here, leading to total n. And if you come over to my definition of the n-ality, you will see that that means that the n-ality of the adjoint is 0. So the adjoint representation is charged under the center of SUN. And so if we think about our screening discussion, but in a non-abelian way, we would say that screening adds multiples of n boxes. So can't modify the n-ality. So what we have learned from this is an extremely important conclusion. The important conclusion is that SUN Yang-Mills has a ZN1 global symmetry. Notice it's discrete. There's no current. So I've told you above how it acts on lines, but let's say it again. So here we have some Wilson line, L, and here we have our U surrounding it. And we're in 4 dimensions, say. So this is an Q. And this is the exponential of I alpha times the n-ality of L, the line. And of course, here alpha is 2 pi k over n for some integer k. So that's how U alpha acts on the charged objects. Are there questions about this?
Sorry, maybe I did not follow, but in the earlier case, the U alpha acted on it. In the free case, the U alpha was acting on it with the exponential I alpha QL, which was the charge under the U1 electric gauge group. Here we are looking at pure Yang-Mills, right? So first of all, I did not understand why the statement about screening, and then I did not understand why here we have the n-ality showing up instead of just, let's say, the charge under SU, and maybe I'm missing something.
Good. So there are a variety of things that we've put together here. So first of all, coming back to the abelian case, the charge under U1 of a Wilson line, so the electric charge is an integer. So it makes sense to measure that charge. And indeed, that's what happens in the free Maxwell theory. Now, the discussion about the screening, which set us up for the non-abelian case, that discussion was to say that if you have some dynamical charged things, say of charge Q greater than 1, then it doesn't make sense to ask about the integer electric charge of a line, because that is distance dependent. Instead, it makes sense to ask about the charge modulo Q. So that's how we got to this statement that the one form symmetry will be, in fact, this ZQ group, where Q was the minimal unit of charge in our problem. Okay, now we wanted to combine those to understand what's going on in non-abelian gauge theory, SUN Yang-Mills. And of course, a big difference between abelian and non-abelian gauge theory is that non-abelian gauge theory is already interacting. There's already something charged in the Lagrangian, right? Namely the gluons. The gluons are charged. So here we went through a discussion where we saw, first of all, what is the meaning of charge under SUN? The meaning of charge is a representation. So some Young tableau, if you like. And we'd like to know what can we measure for this chart, about this charge, and which part of it is a conserved quantum number, or which part of it is distance independent. And in order to figure out which part is distance independent, we need to figure out what can be screened by the matter that we already have, the charged matter, and that's the gluons. So the gluons are in adjoint representations, so they can screen anything with anality zero, because the gluons themselves have anality zero. So what we get to from this line of reasoning is that the conserved quantum number, the thing that is really a charge that we want to study, is the n-ality, the charge, the number of boxes modulo n. Because we can always add multiples by putting in lots of gluons. And so that's how we got to this final statement.
I see. Yeah, that was quite clear. Yeah, thanks. Yeah, it's the self-interactions basically.
Yes, exactly. We have to take into account the self-interactions from the beginning now.
Exactly. Thank you.
Yeah, more questions.
So let me ask a question. It looks a little bit like a necessary but not sufficient condition. Is it, I don't know if you can comment on that. Is it sufficient to have this?
No, it's not. If given more time, I would, and I did something like this in the discussion section yesterday, I would explicitly exhibit for you the transformation on the fields that defines U alpha. So U alpha, one thing that I bypassed in this discussion of symmetry is in the usual sort of pedestrian discussion of symmetry that you see in a book, you see that, okay, you start with some action on the transformation on the fields that leaves the action invariant. Then you turn some crank and get something like a current. And you can build the charges out of that. And you could say, well, isn't there a starting point like that for these higher form symmetries? And indeed there is. And I would have to sort of show you a transformation on the non-abelian gauge fields that leaves the action invariant. So that also exists. And that really justifies the construction of the U alpha. So I didn't really say, like, what is U alpha as a function of the fields, for instance. But the reason I'm not going through that is that, well, we would not get anywhere else, basically. But anyway, this is kind of the heart of the matter, the Zn.
Sure, we can save it for discussion session.
Yeah. Well, I mean, it was in there for the abelian case yesterday, so the non-abelian case is very similar.
Thanks.
Okay. Questions? Okay, well then let's keep going. Okay, so why care about this Zn one-form symmetry? Why study it at all? So there's a very important connection to which I'd like to go over for you. So this one-form symmetry gives us a way to understand gauge theory phases. By symmetry. So something like a Landau paradigm. So, there's this nice Landau paradigm of phases where you think about, you have some global symmetry and you can talk about a phase where that global symmetry is spontaneously broken or not. And for a long time, the most prominent gauge theory phases like confinement or other fancier forms of confinement resisted such a definition. But what I'm going to tell you is that if you allow yourself to think in terms of these one-form symmetries, then they are very similar, these phases. So in particular, what I'd like to show you or motivate for you is that this Zn1 one-form symmetry being spontaneously broken is the same thing as saying that the theory is deconfined. And the other option, namely that this Zn1 one-form symmetry is preserved by the vacuum, is the same as saying that the theory is So let me try to motivate these statements. So these statements, these phases are usually phrased in terms of perimeter versus area law. So we draw a fundamental Wilson loop, which looks a little kind of rectangular in shape. And we look at its expectation value. So this is a fundamental Wilson loop. This direction is T. This direction here, this separation is R. And we look at R big but T bigger. So we have sort of two characteristic behaviors. If this goes like e to the perimeter, then one says that the theory is deconfined. Or if it goes like e to the minus area, one says that the theory is confined. And of course, the motivation for this is that this fundamental Wilson loop can be interpreted as the potential between probe quarks, quark and anti-quark. And so you're getting a sense of the energy cost of trying to separate quarks a long way. Okay. Now, in this limit here that I identified, you can actually view this fundamental Wilson loop as a sum of two pieces. Well, sum of lines, let's say. And really the long parts, the time parts really matter in this discussion. So in the case of confined, what we would determine is that this infinite Wilson line, let's write it like this, the expectation value of the infinite Wilson line that this would vanish. So if you think about confinement just in terms of an infinite segment, infinite Wilson line, means that the expectation value of that is 0. And if you think about the deconfined case, it means that the expectation value of this infinite Wilson line is not 0. So let's understand why this is related to symmetry. So this infinite length Wilson line is charged under a one-form symmetry. That was Zn1 that I identified for you above. Which generally look at? Well, we should look at U alpha of sigma, where sigma intersects this line once. So remember, this is how we think about things in the Hilbert space interpretation that we talked about yesterday. So what we see is that these phases are distinguished by a charged object having a vev. And this is, of course, the hallmark of spontaneous symmetry breaking. So to repeat the basic conclusion, we should think through this this reasoning more, but to repeat the basic conclusion, one-form global symmetry in gauge theory is essential because it is the way of diagnosing these fundamental gauge theory behaviors, namely whether you are confined or deconfined. You're confined if you preserve the one-form global symmetry. You're deconfined if you spontaneously break it. Okay, I'm going to move on to another topic, so perhaps it's a good moment for questions.
Lucas?
And so I have a question. I don't understand quite well why you separate the two lines and just said that the expectation value of a line is 0 if you got a confinement phase. I mean,
because this is going to 0 in the limit where I take sort of the thing infinitely long. So, you know, in the limit where t gets very big, the most important contribution, the part that we're focusing on, is just this very long, the two very long sides.
yeah, just understand.
Yeah, and so I'm saying in the limit here, for the confined case, just says that those two the whole loop goes to 0, so the two sides also go to 0, because we can reconstruct the loop from the two sides. In the deconfined case, okay, there's a little caveat that I didn't mention, which is that the perimeter law, this can be absorbed by adding a counter term on the line. You see, because it's proportional to the perimeter, you could write something local on the line that would modify the definition of the line to make it constant. So then the deconfined phase, it's easier to think about after you add that counter term on the line. And then the deconfined phase would have the feature that the loop has constant expectation value in this limit.
Yeah.
And then you see that in the limit where you think about it as just the two long pieces, it just means that the infinitely long piece is non-zero.
Mm-hmm. Okay, so this case understand, but in the confined case, get 0.
Yeah,
so
exactly.
What? So it's because you can renormalize this operator. Why? I mean, what is going on? even if you renormalize this line,
you can renormalize it by something. You can renormalize it by anything that's local on the line. So you can renormalize it by something that scales like the perimeter, but not by the area.
Ah, okay. Nice. Okay, thank you.
Any more questions? Okay.
I have a question, sorry.
Yeah.
Could you say just a few words about the magnetics one-form symmetry in the non-abelian case?
There is none. Well, at least for SUN, there is none.
Yeah, can I see that you have it for SUN was the n, say?
Well, the question is really about the 't Hooft lines, if you like. The kind of, what are the monopoles that you have? So there's some, just as we went through some group theory to discuss what the electric charges are, the Wilson lines, there's some corresponding group theory for magnetic charged objects. So maybe that's a good topic for the discussion section, because it would take us a little while to do that group theory, but there's a completely parallel discussion here to what I did here, but for the magnetic charges.
Okay, sure, thank you.
Yeah, please come to the discussion and ping me about it, and I'll explain it in detail. Okay, any other questions? Okay, so for the last 20-ish minutes, we're going to talk about a new subject. We're trying to get to anomalies and using these notions of symmetries and anomalies to get to some dynamical conclusions. And a piece of technology that we'd like to use is the notion of source gauge fields. So this is a kind of complementary way of thinking about the idea of symmetry to the U alphas, and they're really kind of on equal footing. And so when you discuss source gauge fields, what you're going to do is you're going to probe. Okay, that's a B in there. Probe your theory with a gauge field, a background gauge field. So we'll start with the situation that we're most familiar with, that is ordinary global symmetry, continuous, and we'll build up as we go. So we would modify the action by including something like A mu, J mu, and J, of course, is our conserved current. So it cannot be stressed enough times that in this discussion, A is a classical background field. So often when you see the word classical in this quantum field theory literature, what it means is that it is not summed over in the path integral. By contrast, saying that A is a quantum field would then mean that it is something that I have integrated over. Of course, our integral, path integral over the actual fluctuating fields this defines a partition function. And it's a function of A, this background source. And you can think, as you do in your first QFT class, that at least in the first approximation, what this is good for is that it's a generating function of current correlation functions. Okay. So we'd now like to discuss what is the right notion of gauge fields for more general types of symmetries. So this is our main question that we would like to answer. So there are two things that two kind of generalizations that we need to introduce. The first is that when I wrote this example with A coupling to J, I have in mind, of course, a continuous symmetry. I even wrote it in a kind of abelian notation. So you could have in mind an abelian continuous global symmetry. Of course, we know what we're doing also for non-abelian continuous symmetries. But one thing that perhaps is unfamiliar to you is what should you do with a discrete symmetry? What is the right notion of a background source? Gauge field. And the second generalization is, of course, the higher form global symmetry. So what is the right notion of gauge field for a higher form global symmetry? And of course, that last question can come in a continuous variety and in a discrete variety. So let's start with the discrete case, and let's stick for a minute to zero form gauge fields. So let's let G be a discrete. You will lose nothing if you just think that G is Zn. So what is the correct notion of a background gauge field for a zero form symmetry G? A background gauge field for G, well, what should it be? It should be an assignment of holonomy G in G for each one cycle gamma in space-time. So what is being asserted in this equivalence? One thing that's being asserted is something that might be a little bit unfamiliar, which is that a discrete gauge field is flat. There's no analog of a curvature for a discrete field. A curvature is something that is, you measure infinitesimally. And there's no analog of that. There's only global features. So if you have a Zn symmetry, there's no curvature for your background gauge field to study. The only thing you have is the holonomy, the phase that you assign when you go around a cycle. And so that's what's being asserted here. So mathematically, we could say that the gauge equivalence classes let's call it square bracket A, that this is an element of a cohomology group. So this is space-time. This is the first cohomology. This is cohomology valued in G. So what does it mean? So cohomology class is something that eats a one side. One because this is a superscript one, so it eats a gamma and gives us out an element G and G. It has two properties. It's closed. So the exponential of I integral of A along gamma. This is something that we can ask. We can ask what the holonomy of A is along gamma. That's what I'm doing here. This is 1 if gamma is a boundary. And we also mod out by gauge transformations. So if you've never seen this before, fear not, because the definition is literally on the board right now. So now the same idea, oops, we need a new page. The same idea works for Q-form symmetries. So now we will introduce a background field. I'll call it B. This will be a Q+1 form. You should compare that to the case Q equals 0, which was an ordinary global symmetry, and the background gauge field was a 1 form. And now, instead of being characterized by these holonomies, these Wilson lines, the gauge field will be characterized by Wilson surfaces. So what we will do is we will study the Wilson surface, which is the exponential of I times the integral of B over any Q+1 cycle gamma. And what this means is that the gauge equivalence class of this gauge field is in HQ+1 of M with coefficients in GQ, where here this is the Q-form symmetry of your theory. So maybe to bring it back to the partition function, we're used to saying that the partition function Z is a function of the sources. In this case, it will depend on, say, B, if we had a theory with some Q-form global symmetry. Okay, maybe ask me questions about the general formalism, and then I'll start doing some examples.
Antonio, you
Yeah.
can.
Can you just phrase this in the case of a continuous global symmetry? Does it make sense to say fix the holonomy, but then you would also have to take into account the continuous part? Or
Yeah, so maybe it's worth emphasizing this caveat again. So the caveat is that this discussion is correct for discrete higher form fields, higher form symmetry. For continuous symmetry, we need more. There's also curvature. Now that brings me to my first example, which maybe I will do. So you see, the continuous and the discrete cases can be treated basically separately, because the continuous cases are not so common. They're mostly associated with free fields of various sorts. So in the kind of crucial applications of the higher form global symmetry, it's really the discrete cases which are the most interesting. But let me also do this example since we brought it up. So let's do 4D max. Again. So we had, remember, this one form symmetry, which was U1 electric 1 times U magnetic 1. And there was a current here the current was nu, and here the current was star F mu nu. Now, for continuous symmetries with currents, it should be more obvious what we mean by the right background field. So the action coupled to background fields. So of course we have F mu nu, but then we also want to B mu nu E F mu nu plus B mu nu M times star F mu nu, where here BE and BM are two-form background gauge fields. Now they're continuous, so dB is not 0. And these are the curvature parts that one would need to take into account in general for the continuous case. Now, they're background gauge fields, meaning that they enjoy a gauge redundancy. I can shift B, E, or BM by the exterior derivative of lambda, where this now is a one-form gauge parameter. So that's, if you like, the most concrete simple case to deal with. So in this case, the partition function Z would be a function of these two background gauge fields, BE and BM, after integrating out the dynamical gauge field. And we would want to study properties of this partition function to understand correlation functions of F and star F, for instance. I emphasized the discrete situation in a sense because this example is sort of the example with continuous one-form symmetry. So it's good to sort of bite the bullet as soon as possible and get used to dealing with these discrete background fields. Okay, more questions?
Lucas, please.
Yeah, so this curve gamma, you define it's not supposed to be closed, right? It's an open curve.
Gamma? No, gamma's closed. Gamma? It's closed.
It's closed. So, I mean, upstairs.
We're talking about the whole anomaly. So, we want to consider some topologically non-trivial loop, say for this case, and we want to ask what phase does the gauge field produce when we wind around that loop. Here, we're talking about the same notion, but on a surface, where by surface I mean something of dimension q+1.
Okay, thank you.
Okay, I see that I'm out of time, so maybe I'll just continue with questions until I'm booted.
Okay, so let's thanks Clay for the very nice lecture. And if there are more questions, please. So Antonio, please go on.
Sorry, continuing my question, and this is probably kind of silly, but does it make any sense to say specify the holonomy and then integrate over the continuous part, like just have as a parameter in the path integral?
This is a good question. You usually have to have kind of a hierarchy of thinking when you're thinking about gauge fields. So when I say that for a discrete gauge field, you only have to think about this cohomology class. This is intrinsically using the fact that there's no curvature. Because one thing it means is that if you wiggle this surface, gamma q+1, a little bit, the phase you get from this Wilson surface will be the same. On the other hand, if there was curvature, so in this situation, where you have the continuous fields, then wiggling, if you ask about, you can still ask what is the integral of B over some surface. That's a perfectly legitimate question. But B is not in general closed. The derivative of it is not 0. So if you wiggle that surface a little bit, you'll just get a different answer. So usually one discusses sort of holonomy of gauge fields only for flat gauge fields. And or at least that's the setting in which it makes the most sense. And here, what I'm trying to emphasize to you is that all discrete fields are flat, meaning there's no curvature.
Right. I mean, I was wondering if we could basically flatten out curve gauge fields by path integrating the continuous path in the path integral and fixing the holonomy, but maybe this
not in a way that I know of.
I see.
And just to come back to that point, it's important that these B or this B, these are fixed. We're not going to integrate over them. We'd like to examine the partition function thought of as a function of these sources.
Thanks.
So Enrico, please.
Yes, sorry, I haven't understood the last 3 lines. Because that action clearly is a gauge invariant under the last transformation you wrote and the last line, only on shell, right? But I mean, usually you should couple like the gauge fields in a gauge invariant way that is also gauge invariant also of shell, right? Or I'm wrong?
You're maybe complaining that I didn't add a BE squared term, but that is just some counter term.
No, I mean, if you do the gauge transformation that you wrote.
I mean, yes. But I didn't tell you how A transforms. So I can assign any transformation property I like to A because it's being integrated over. And so A will shift under the lambda E gauge transformations. So if you like, what I should have written is well, minus BE squared plus BM times mu nu times F mu nu. So the difference between this and this is just a BE squared term, which I omitted on purpose because it's a little bit confusing to explain. But this is manifestly gauge invariant if I assign if I assign A to shift under the gauge transfer, which is just to say that that this U1 electric symmetry is spontaneously broken by the in this theory. So going back to our confinement deconfinement discussion, the expectation value of the Wilson line is non-trivial. The photon shifts under the transformation, so it's like this kind of Stuckelberg mechanism, and the photon is the Goldstone boson for this spontaneously broken symmetry.
Yeah, I see. Okay, thank you.
Yeah.
So Tushar,
So I just had a small clarification. So this exponential of I integral A on gamma, why is this one? I mean, naively, I will think that just naively that.
So if gamma here.
Yeah.
That's the statement that A is flat, right? Usually, if gamma is the boundary of something, you would use Stokes and take the derivative inside and say, well, this is the same as integrating dA over sigma. But for discrete gauge fields, everything is flat.
Okay. We do not have the curvature. So
there's no curvature. There's no notion of curvature to talk about.
Okay, fine.
So Wayne?
Yeah, just a related question. So for the Q-form symmetry, then if we have a closed gamma cube plus 1, then it's also 1. But if it's discrete.
You mean if gamma is a boundary? Yeah. Uh-huh.
Yes, if it is boundary, yes.
If gamma is a boundary, then yes.
If gamma is a boundary. And then if it's continuous, then it's potentially not 1, and because it's not flat.
That's right. Yes.
Okay.
Yeah.
Okay, there is also a question on the chat. It's Kaan. Maybe you can. The question is just going back to the confinement discussion. Does the lack of one-form symmetry mean QCD is not confined in this sense?
That's an excellent question. So, this gives a very nice way to say when is there a meaningful notion of confinement. And since indeed, for actual QCD, here we just did pure Yang-Mills, so we had this Zn one-form symmetry, but if we had dynamical quarks, we would break this to nothing. Just because of our screening discussion again. And so then there would be no symmetry by which to organize these phases, and indeed it's believed that there's no sharp distinction between a confined and deconfined phase in QCD. So that matches very nicely, actually.
Okay. I think there are no more questions. No, there is, I think, the last one by Akiho. Please go on.
Hi. Could you repeat that comment about the photon being the Goldstone boson, and could you also remind me what should I think took the wave?
So the question was repeating the comment about the Goldstone boson, if I understood correctly.
Yes, right. And
yeah.
What took the vacuum expectation?
Wilson line. The Wilson line is a non-trivial operator at long distances. Right? If something is spontaneously broken, something charged has an expectation value. The charged things are lines. The comment about the photon being the Goldstone boson. Well, one way to see it is that if you really want me to get right the invariance of the action, I have to write it in this kind of completing the square way, where I assign the gauge field A to shift under the lambda E gauge transformation. And what that means is, think about what that means. That means A is shifting under the symmetry generator that we're talking about. So it is a Goldstone boson.
Okay, thank you.
Okay, so let's thank Clay again. In fact, I think that is time for. There is one more question on the chat. Is it okay?
Is there any sense in which you can apply this formalism to gravity? Excellent question. It's not. Nobody has succeeded in doing that. But there's no obvious higher form symmetry of gravity in this language. But one gets the feeling that perhaps a slight generalization of the concepts presented here could apply in a more broad context, including gravity. So I think it's a very good question.
Okay, so thanks, Clay. Thank you, everybody, and
see everyone tomorrow.
See you tomorrow for the last day of the pre-strings. Okay, thank you.